Ever since tanks thundered onto the battlefield in World War I, it's been a high-stakes showdown. Armor versus firepower. Every time a tank gets tougher, weapons get nastier. Tank makers scramble to shield their machines, while weapon experts cook up rounds designed to break through. So who's winning this never-ending game of rock, paper, scissors, and what could come next? In this video, we're diving into the wild world of tank armor and the weapons built to take it down. Let's kick things off with the tanks themselves. Tanks were born out of necessity, designed to smash through the deadlock of trench warfare in World War I. While they wouldn't protect against artillery, their thick rolled homogeneous steel armor would defend the troops inside and behind them from the machine gun and small arms fire that cut down swathes of men as they attempted to storm an enemy trench. Tanks were primarily a weapon used by the British and French. Because of the Allied naval blockade, Germany found it challenging to get the materials to build its own tanks. Only 20 of the German A7V tanks were produced, although they proved to be high quality. Germany instead focused on making specialized anti-tank weapons and capturing Allied tanks for its own use. To counter the early tanks, the Germans developed a huge anti-material rifle called the Mauser 1918 T-Gewehr. This was a bolt-action rifle that fired a 13.2mm armor-piercing steel core cartridge. The gun was so big that it required a 5-man operating crew. To compensate for the huge recoil, the rifle had a foldable bipod that spiked into the ground. It could only be fired from a prone position, as anything else would be unsafe. The muzzle velocity was 3,000 feet per second. The high velocity and steel core meant the anti-tank round could penetrate 20 millimeters of steel armor at a range of up to 100 meters against a 90-degree surface. Since Allied tanks were designed to protect against small arms and machine gun fire, their armor only had a thickness of 12 millimeters, which meant the German rifle generally fared well in combat, and it set the precedent for anti-material rifles that continue to be made today, although these are no longer effective against vehicles as heavy as tanks. The same basic tank technology carried over into World War II, but the armor got thicker. Between the wars, it became apparent that tanks would need to be better protected against anti-material rifles and, more importantly, other tanks. Like before, tanks had a frame of rolled homogeneous steel with varying thickness depending on the tank, but the armor was in all cases much thicker than their World War I predecessors. The American Sherman, for example, had armor that was 76 millimeters thick at the front. The Soviet T-34 ranged between 16 and 60 millimeters. Germany's tanks tended to have heavier armor. The Tiger I had armor between 100 and 120 millimeters thickness. The increased thickness was required to defend against more powerful tank guns. The Sherman's main gun was 75 millimeters, as was that of the German Panzer IV. The T-34's main gun was slightly larger at 76.2 millimeters. The German heavy tanks sported much larger guns. The Tiger I had an 88mm gun, derived from the famous Flak 88 cannon. The Tiger II had the same gun, but it was longer, meaning it had a higher muzzle velocity. In addition to these newer, more powerful tank guns, anti-tank weapons also got stronger in the hands of the infantry. Rocket weapons with shaped charges began to appear on the battlefield, like the American bazooka and German Panzerschreck. These shaped charges focused their warhead's energy in a way designed to defeat armor. So although tanks got thicker armor, the heavier steel wouldn't be enough to defeat many anti-tank rounds. The 88mm cannon, especially the Tiger II's, was particularly effective. The Tiger's main gun was specifically designed to beat the armor of the T-34. Anti-tank weapons wielded by infantry also needed to be accounted for as armorers plied their trade. To increase their effectiveness in the face of these more lethal challenges, tanks also started to have armor that sloped at varying angles. The principle was the same as that seen in the construction of fortifications after the invention of the cannon. Previously, straight walls proved inadequate in defending against sustained artillery bombardment, so fortification engineers made their walls thicker, lower, and more angled. The angles ensured that much of the energy from an impacting projectile would not be transferred to the target because they would not suffer a direct hit. The same became true with tanks. The angle of the frontal plate increased the effective thickness of the Sherman's armor from 51mm to 91. The angled slopes increased the distance incoming shells would need to travel before penetrating the plating if they did not bounce off. Thus, they would lose much of their energy. The T-34's slope of 60 degrees vastly increased its effectiveness. Many incoming anti-tank rounds glanced off of this armor. To penetrate rolled homogeneous armor, one would fire various rounds that used kinetic energy to puncture the target tank. From there, they would fragment to destroy the tank's interior and crew. The aforementioned 88mm cannon was the German solution for this problem, particularly against the T-34. However, as tank armor improved, these basic rounds started to lose their effectiveness, particularly at longer ranges when their kinetic energy decreased as they reached the target. Many such weapons were already proving ineffective against the German Tiger tanks. The Sherman's main gun, or bazooka for example, could not deliver enough punch to penetrate its armor in most circumstances. Artillery or close air support proved the only reliable way for American and British troops to combat the German Tigers. So anti-tank weapons began to change, with different rounds appearing to counter more formidable armor. One of these is the high-explosive anti-tank, or heat round. Heat rounds have an interior that's lined with a soft metal like copper. Upon impact, the warhead explodes, which collapses this liner into a high-velocity jet of molten metal up to 7 times the size of the original round's length. The jet breaches the interior of a tank and cooks whatever's inside. As these rounds don't rely solely on kinetic energy, range is not as big of an issue, and they can be fired more accurately from a tank gun since there's less recoil. Another method of piercing thicker, angled steel tank armor is through the armor-piercing discarding sabot round and its successor, the armor-piercing fin-stabilized discarding sabot. This is also called a subcaliber round because the sabot is a thinner projectile placed within the casing that ensures a tight fit in the tank's gun. Once fired, the casing discards, leaving only the thin dart flying towards its target. Some of these rounds are made of depleted uranium or tungsten, which makes them very dense. Since these rounds use kinetic energy, they are fired with high muzzle velocities up to 1,650 meters per second or more, a speed of roughly Mach 5. The combination of hypersonic velocity, small size efficient for concentrating energy, and their dense construction makes them good long-range penetrators. A third type of anti-tank round is the HESH, high-explosive squash head. These rounds use plastic explosives like C4 to conform to the surface of their targets before they detonate. This adaptation improves the transfer of energy from the round to the target. These rounds don't penetrate armor like heat and sabot rounds do, but the shockwaves they create when they detonate so close to the tank can cause injury or death to the crew inside or damage the tank's internal machinery. Since ancient times, armor has been a trade-off between protection and mobility. During and after World War II, tanks got thicker armor, but without sacrificing mobility, thanks to their more powerful engines. However, it would be impossible to create rolled homogeneous steel armor thick enough to defend against these new anti-tank rounds, even with improvements in engines. Doing so would mean creating an immobile tank, so armorers needed to come up with a new strategy. One of the solutions was to create separate steel plates located at a slight distance from the tank's mainframe. These separate plates might not seem like much, but incoming anti-tank rounds quickly begin losing their energy upon impact. Putting something in front of the tank gave the mainframe more survivability, since the incoming round would now be less powerful. Even the molten jet from a heat round cools down rapidly, so if it impacts a protrusion in the front of the main body, its jet is less likely to get inside the main tank. However, arms manufacturers responded to this development with more powerful tank guns that could, in turn, fire more energetic rounds. The spaced armor was good, but not enough to withstand a direct hit from a projectile fired by something like the Soviet T-54 tank with its 100mm gun. Since their debut in World War I, tanks had been made of steel. That now began to change and composite armor appeared on the battlefield. This armor made its debut with a tank that might sound Russian, but was actually American, the T-95. This tank never entered service, but it started a trend. Steel would be the base of the armor as usual, but between the steel plates there would be silica glass. Silicon carbide or aluminium oxide can be parts of composite armor too. These composite materials add to a tank's volume, but they are lighter and can withstand similar impacts, so the net result is actually an improvement in mobility. The steel backing behind these composite ceramics prevents them from shattering. The Soviet T-64 tank used polymers for its composite armor, hardened plastics that were flexible and absorbed additional energy when something hit it. Modern tanks like the British Challenger and American Abrams use hard ceramics in their composite formulas. These tanks also use depleted uranium inserts for extra protection. This material's density makes it extremely challenging for an incoming round to penetrate. These substances proved effective not only against fire from other tanks, but also anti-tank guided missiles and even air-to-surface missiles. To penetrate this armor, the armor-piercing, fin-stabilized, discarding sabot round became a tank crew's weapon of choice. Heat rounds were designated for other purposes, which is why they're often called Heat MP, multi-purpose rounds today. Sabot rounds have adapted their designs over time to account for more flexible and denser armor. For example, to counter improvements in NATO armor, the Soviet Union created a sabot round with a tungsten slug hiding behind a hollow ballistic cap. Upon impact, the hollow cap discards to allow the much denser tungsten slug to continue on its journey. This was an ideal round to penetrate the flatter armor designs that NATO tanks were using. To combat Soviet and Russian tanks, the United States uses a depleted uranium sabot in a long rod that gains penetrative power when it hits the kind of sloped armor that Russia had long used in its tanks. Because of the sloped armor, there is less of an area of solid material around to stop the penetration of the incoming sabot. Even if it doesn't make it through the innermost steel plate, the dart can still damage the tank's crew or machinery. Against a flat target, though, the American long rod sabot round would have less penetrating power because of its length. The British sabot rounds have a clever design, a notched tip, which makes them effective against both flat and angled targets. They also have both flat and conical tips, depending on the target. But even with the composite materials, the aforementioned spaced armor never went away, and here's where it becomes important. Spaced armor became part of the layers of composite material. Strange as it may sound, empty air is an important component of a modern tank's composite armor. An incoming sabot can skew off course and lose energy if it has to penetrate multiple gaps of air between armored plates. If there was solid material, on the other hand, there would be nothing to divert the incoming projectile from a straight trajectory, and more penetrating energy would be retained. As tank armor became harder to defeat, both NATO and Soviet weapons began to try targeting more vulnerable areas. This is a particular problem with Soviet and Russian tanks, which leave their ammunition exposed. We've all seen what that means on the battlefields of Ukraine. NATO troops were often directed to target the hull of a Soviet or Russian tanks to cause just that jack-in-the-box chain reaction. A tank's turret is thinner than the main chassis, so Western armorers began to improve the armor up there, since Soviet and Russian anti-tank rounds were designed to target them. More depleted uranium layers were added to prevent anti-tank rounds from penetrating. However, these improvements mean that the Abrams has now gotten a turret so heavy that it's increased the tank's weight to over 70 tons, prompting fears that it's becoming too cumbersome to maneuver in battle, or even to effectively transport to the battlefield in big numbers. The tanks of Western turrets in general began to move their tank turrets toward angle designs too, as a way to counter Soviet sabot rounds that were well suited for penetrating the previously flatter designs of NATO tank turrets. The trend started with the British Challenger, which proved its worth when it devastated the Soviet tanks Saddam Hussein's army used in the Gulf War. But as always, tanks do not only face threats from other tanks. Tank versus tank battles have been rare in Ukraine, for example, and during the War on Terror, tanks would most frequently come under attack by ambushing infantry, using portable anti-tank weapons like RPGs. Handheld anti-tank weapons have become more accurate and powerful with the years. The Russians learned that the hard way during the wars in Chechnya in the late 1990s and early 2000s, when rebels armed with RPGs sent many T-72 and T-80 tanks to the scrapyard. Now, small, fast-moving drones add yet another challenge to armorers working to keep their tanks and crews safe. Reactive armor is one of the answers to the increased threat from both tanks and infantry. This armor comes in panels that are installed outside the tank's main body. Reactive armor is designed to disrupt incoming projectiles by, as the word implies, reacting to them before they impact the tank's main body. The most common of these is explosive reactive armor, ERA. These are panels with an explosive substance installed between two steel plates. When an incoming projectile hits these panels, they explode, disrupting their forward momentum. This type of armor is even effective against sabot rounds because they can knock them off course or in some cases even break the rods apart. Against heat rounds, the incoming chemical charges are diffused. Non-explosive reactive armor, NERA, produces a similar effect without an explosion. Modern ERA has also been designed to reduce its explosive area to minimize collateral damage, which is especially important for battles in urban environments, where infantry and tanks must operate closely together. ERA was first conceived in 1944, when the Australians thought of using explosive substances to counter the effects of the Japanese 75mm shell. The Australians tried to counter the resulting jet of molten metal liners in the shell by either blowing it apart with explosives or using an oxidizer to burn it out before it reached the main body of the tank. The Australians had mixed results and the war ended before they could take it any further. In 1949, a Soviet-Ukrainian scientist named Bogdan Vyacheslavovich Wojciechowski came up with a similar idea, but his results proved inadequate and the idea was abandoned as tank armors improved. But as anti-tank weapons got more powerful by the 1970s, the idea of ERA again proved intriguing. A Norwegian scientist named Manfred Held registered a patent in West Germany in 1970, but the real breakthroughs came from the Israeli experience in Lebanon in the early 1980s. The Israelis hired Held to work with their armorers to develop ERA, and in 1982, the Blazer became the first model that saw widespread deployment. The Israeli tanks became much more survivable as a result, and militaries around the world quickly adopted their own versions of ERA. By 1990, all major militaries were attaching it to their tanks. To make matters better for armorers, ERA is extremely weight efficient. It can be attached without compromising a tank's maneuverability. For example, a T-72 can be made much more survivable with a total of 2,700 kilograms of attached weight of ERA. Since the tank has a total mass of about 41,000 kilograms, this is greatly increased protection without adding a noticeable additional mass burden. ERA can also be positioned at different angles to create different detonation times and positions. ERA is most effective when an incoming projectile hits the block's bottom and least effective at the top. Armorers can position their blocks of ERA according to the likely angles of the anti-tank projectiles their units will most likely face. NERA operates by using blocks of elastic or other materials that produce similar effects as ERA. These materials divert the energy of an incoming projectile without exploding. NERA is even lighter, but isn't quite as effective. It is, however, ideal for operations where tanks and infantry will be in particularly close quarters with one another, such as certain urban combat scenarios. There is a third type of reactive armor undergoing testing, electric armor, EA. Like its older siblings, it uses two steel plates as a base, but the layer between them is filled with an insulating material possibly as simple as air. This material divides the two plates, which are electrical conductors. Upon impact from a projectile, the electric circuit between them is closed, which creates an electrical discharge that vaporizes the incoming round. This type of armor has not been fielded yet. There are disadvantages such as a minimum coverage area required for it to be effective and high vehicle power requirements. But given its advantages of being even lighter than NERA and having the ability to take multiple hits when ERA and NERA can only take one, there is an incentive to continue with the experiments. However, as anti-tank rounds have become even more sophisticated, even reactive armor might prove inadequate. Modern weapons like the Javelin can specifically target vulnerable areas of an enemy tank and fly on trajectories that make defense difficult. This is why tanks have begun to integrate active protection systems. These are divided into hard and soft kill categories. Hard kill components use things like interceptor grenades to destroy incoming projectiles at a safe distance from the vehicle, or a network of distributed static effectors around the vehicle that detonate to defeat a projectile that's close. Soft kill components are tasked with diverting incoming projectiles. Such methods range from simple smoke screens that can prove surprisingly effective against infrared-guided munitions to sophisticated jammers. The latter is proving particularly critical for countering the increasing threat of enemy drones. The Russians have tried to use these jammers on their T-72 tanks, but without much success so far. However, it's only a matter of time before tanks with more effective jammers appear on the battlefield. Both tanks and anti-tank weapons have come a long way from their origin in World War I. Tanks have become sophisticated, composite fortresses with smart systems to ensure their survival. Anti-tank weapons have transformed from simple steel slugs to guided projectiles that can seek out their target's weak points. However, these evolutions have only come so that they can continue to fulfill the same mission they had over 100 years ago. Tanks must move forward and create breaches in enemy defenses, protecting their crews and the infantry behind them. Anti-tank weapons must halt the forward momentum of these machines and ensure the defenses hold, if not open the way for a counterattack with friendly tanks at the forefront. What's coming next in the evolution of tank armor and anti-tank weapons? Let us know in the comments. Also, make sure to hit the like button and subscribe for more military analysis from military experts. Now, go and check out Analyzing the Power of Western Tanks in Ukraine, or click this other video instead.